Welcome to Tomorrow Unveiled, the deep dive into the technology that is changing our world right now. Today, we are strapping in for a massive subject. Our mission is to analyze one of the most profound and sudden shifts happening in technology right now, the transition of wearable devices. From passive data collectors, the things that just count your steps and track your sleep.
Right, the Fitbits and early smartwatches.
Exactly. Moving from that to systems of active human-computer integration, or HCI. We're calling this the strapped-in era, maybe the integrated era, because these devices are no longer just accessories or monitors. They're rapidly becoming literal extensions of our nervous systems, our cognition, even our physical abilities.
That's absolutely the core transformation we're seeing. If you trace the history of computing, like the research team that compiled this information did, you see this really clear evolution. Computing started way out there, right? Huge mainframe computers.
Miles away, physically separate.
Totally. Then it moved closer desktops, the mobile phones in our pockets, and finally wearables. That brought the device right onto the body, physical contact. But this integrated phase, well, that's the real inflection point. This is where the circle representing the user and the circle representing the device start to seriously overlap.
Okay, so more than just touching the skin.
Much more. It means the device can sense far more than just basic movement or heart rate. It's potentially gaining access to the user's true biological signals, physiological state, maybe even cognitive intent. And crucially, it gets the ability to act back directly through the user's body.
A closed loop, input and output based on biology.
That's it, a biological closed-loop system.
And what the research team's analysis reveals is really fascinating. This new integrated market isn't just, expanding everywhere, it's aggressively splitting. It's bifurcating into two very distinct paths or vectors, defined by their purpose and, frankly, their risk level. So on one side, you have what they call high-stakes augmentation. These are highly specialized, purpose-built tools. Think environments where precision is everything, maybe survival, or where there's a massive financial return on investment needed, like surgery, defense, or high-risk industrial jobs.
Very specific, very critical applications.
And then on the other side, you have technology that almost paradoxically aims for the exact opposite.
Which is low-friction ambient compute. These are the consumer tools.
Yeah.
And the goal here is to be invisible, silent, seamless. They integrate AI directly into your daily life, your workflow, without needing you to stare at a screen or even push a button.
They just disappear into the background.
Ideally, yes. They dissolve into your life.
Exactly. So our goal today on Tomorrow Unveiled is to unpack the core technologies making this split happen, this bifurcation, and explore the really exciting and maybe sometimes alarming implications for the future of what it means to be, well, connected. Okay, let's unpack this then. Before we get into the really sci-fi stuff like neural interfaces and AR glasses, we have to talk about the foundation, right? The thing enabling all of it.
The silicon.
The tiny silicon engine inside these devices. The fundamental enabler for this kind of integration is the system on chip, or SoC market, but specifically the chips designed just for wearables.
Right, and the growth in this specific hardware area isn't just steady, it's explosive. It really acts as the primary confirmation that the industry is pivoting hard.
How explosive are we talking?
Well, the dedicated research team projects that the wearable device SoC chip market will grow at a massive compound annual growth rate, CAGR, of 9.6%. That's from 2025 projected all the way out to 2035.
Wow, 9.6% CAGR for a decade. That's huge for a hardware segment.
It is. And this huge decade-long growth isn't just driven by more people buying basic smartwatches. It's fueled primarily by the demand for really advanced continuous health monitoring features, and crucially, the integration of powerful AI capabilities directly onto the chip itself.
Okay, that brings up a critical technical point, doesn't it?
Yeah.
AI used to live, exclusively in massive data centers in the cloud. You needed constant connectivity.
Always phoning home.
Right. But for these new integrated wearables, whether it's a surgeon's glasses or a minimalist smart ring, that AI has to be right there on the chip, what they call on the edge.
Precisely. The AI in this new integrated world isn't just passively logging your steps. It is actively integrating into the user's real-time physical workflow, or even their cognitive workflow. Think about a device making a real-time health intervention, for example.
Okay. Yeah.
That demands on-device AI implementation, and that's facilitated by specialized processors. You hear terms like neural processing units, NPUs, or application-specific integrated circuits, ASICs. This is edge computing.
But wait a second. If we're shifting all that AI processing power from these vast, relatively cheap cloud data centers onto tiny, highly specialized chips on my wrist or my head, isn't that dramatically more expensive and more complex to design? How do manufacturers square that cost increase with needing market growth?
That's the core economic tension driving this whole market right now. Manufacturers are willing to absorb that complexity and that cost because the benefits of edge computing are simply non-negotiable for true integration. First off, you get real-time responsiveness.
Makes sense.
If an AI is interpreting a really subtle neuromuscular signal from your wrist or guiding a surgical tool with sub-millimeter precision, any delay, any lag caused by sending data to the cloud and waiting for a response, it's unacceptable, potentially dangerous.
Right, you can't have buffering during brain surgery.
Exactly. And second, and this is equally vital for this strapped-in era, is privacy and security.
Huh.
Local processing drastically reduces the need to constantly stream highly sensitive data, physiological data, schedule data, maybe even data about your intent, back to remote servers. If the AI inference, the actual thinking, happens locally on the device, the data is just inherently less exposed. That's essential for building consumer trust and, frankly, for compliance in those high-stakes fields like medicine and defense.
So the move to edge computing isn't just about speed. It's actually a necessary step to make the device truly integrated in a way we can trust with really sensitive data capture. And to pull that off, the hardware itself has to keep shrinking while somehow getting more powerful.
Absolutely. The big focus now is on ultra-low power consumption and dramatic miniaturization. We see clear evidence of this in strategic partnerships, like the one announced between Qualcomm and Samsung. They're co-developing next-gen wearable Southeast platforms focused explicitly on power efficiency and advanced health tracking. Okay. Similarly, you have chip makers like MediaTek unveiling new series, like their MT2600 series, specifically designed for ultra-low power, health monitoring, and running significant AI inference right there on the device.
So the hardware is evolving, and you mentioned smarter AI earlier. How does that fit in?
Well, this hardware evolution, combined with much smarter AI algorithms, lets the industry break free from the old constraints of sensor density. Think about the previous generation of really sophisticated motion capture. You might remember professional systems like the XN's MVN suit.
Oh yeah, the full body suits with sensors everywhere looked uncomfortable.
Exactly. They required covering the user's entire body with maybe 17 or more heavy, bulky, wireless inertial sensors. High precision? Sure, but totally impractical for daily wear or long-term professional use. It was a capture rig, not really a wearable.
Right.
Now, the research team found that thanks to smarter AI and machine learning processing, you can get similar really high-precision results, like the 96% precision reported in one industrial activity recognition study they analyzed using far fewer sensors.
Really? How few?
Well, one analysis confirmed that a minimum of only 5 to 8 sensors is often sufficient to get the lowest estimation error across a whole range of activities involving both upper and lower limbs. The AI algorithms are just much better now at inferring the missing data, understanding the context, meaning the hardware can be dramatically simplified, less bulky, less power-hungry.
Okay, that makes sense. Fewer sensors, smarter software to fill the gaps, which makes wearables actually wearable.
Precisely.
All right, this is where it gets really interesting and practical. Let's dive into that first vector you mentioned. Vector, a high-stakes augmentation. This is the purpose-built tech dedicated to giving professionals, well, almost superhuman precision or control in high-risk, high-value jobs.
And the perfect place to start is the medical field. Consider the SenkXR AR glasses. Now, this is not a consumer headset someone decided to try using in an operating room.
No repurposed gaming gear.
Definitely not. This is billed as the first medical-grade, open-platform, augmented reality system built specifically for surgical and complex healthcare workflows. It's designed around the highest possible stakes, a patient's life.
And the technical specs really hammer home the difference between a consumer gadget and true augmentation, don't they? The system boasts, get this, 0.3 text marker pose accuracy for surgical tracking, 0.3 millimeters.
That precision is astounding, isn't it? And that specific metric, 0.3 text mint, which is finer than a human hair, is absolutely crucial for things like neurosurgery or microsurgery. When surgeons are working with incredibly delicate internal structures, the slightest tremor, the smallest miscalculation can have catastrophic results.
So how does the AR help?
Well, the system dramatically reduces the surgeon's cognitive load. It does this by overlaying critical information like patient vitals, 3D anatomical models from scans, or maybe planned incision paths directly onto the surgeon's field of view in the glasses.
So they don't have to look away.
Exactly. It eliminates that constant need for the surgeon to look away at a separate 2D monitor, which forces them to mentally switch context, refocus their eyes, break concentration. The analysis from the research team notes the goal is simple but profound. Allow the surgeon to see, understand, and act with greater precision. It's literally augmenting their sight and their continuous attention.
Wow. Okay, moving from the sterile surgical suite to, say, a muddy construction site or someone's attic, we see similar high-stakes augmentation, but focused more on efficiency and measurable ROI. Devices like Superglass, aimed at skilled tradespeople, plumbers, electricians, roofers.
Right, and this application leverages a different core HCI mechanism. It's a totally hands-free, voice-activated AI assistant, but it's integrated into safety glasses. The problem Superglass is solving is the incredible administrative burden, the documentation bottleneck that just plagues skilled trades.
The paperwork nightmare.
Exactly. So the AI actively structures the data. It's constantly transcribing and translating, as they put it, what's seen and said into structured job data instantly.
So the worker just talks about what they're doing, what they're seeing.
And the AI handles the note-taking, the report generation, maybe even compliance checks, all in the background. The worker never stops working, keeps their hands on their tools, which enhances safety and efficiency, and the measurable impact. This illustrates the value of integration perfectly. Early adopters reported 40% faster inspections.
40%.
And a dramatic 70% reduction in paperwork time. That's a massive return on investment, built purely on integrating data capture seamlessly into the workflow.
Okay, that's impressive ROI.
Yeah.
Now, finally, in this high-stakes vector, you mentioned something that sounds like it's straight out of science fiction. It fundamentally redefines how we interact with machines.
Yes, the WLDSX TRODES Tactical Neural Interface.
Yeah.
This is a huge breakthrough. It's a fully functional, touchless control system for tactical systems, like drones or communication gear, based on a neural human-machine interface.
Okay, neural interface. This moves way beyond just voice commands or touch screens, right? This is about reading the user's actual intent before they even fully move.
Exactly that. It utilizes the Xtrode's Smart Skin.
Yeah.
It's a high-performance, flexible electromyography EMG patch, often worn very unobtrusively, say, on the wrist. Now, when you decide to move your hand or your fingers, your brain sends electrical signals down your arm to the muscles.
Right, the nerve impulses.
EMG detects this subtle electrical activity, this hum from the muscles before or as the movement happens. Then sophisticated AI classification algorithms interpret these subtle neuromuscular signals, these intuitive gestures, and translate them into digital commands.
So the AI isn't waiting for my finger to physically press a button on a drone controller. It's reading the electrical plan for that action from my wrist.
Correct, or very close to it. And this solves what the military calls a long-standing operational limitation in high-risk tactical environments. The inability to communicate and operate systems concurrently.
Because your hands are busy.
Right. If a soldier has their hands occupied holding a weapon or maybe climbing or performing some other physical task, they can still control navigation systems, communication gear, maybe a small drone, just via these subtle nonverbal signals interpreted right from their nervous system. That is the ultimate move from physical interaction to true neural integration. Mind-blowing stuff. Okay, so now let's pivot. Let's look at Vector B, the other side of this market split. This is the technology designed to be so subtle it genuinely dissolves into your daily life. This is low-friction ambient compute. The main goal here is just reducing interaction friction down to zero, or as close as possible.
And the holy grail in this vector is basically invisibility, isn't it? Making the device feel less like a gadget you have to manage and more like a natural, silent extension of your own memory or perception. The Sandbar Stream Ring seems like the perfect example of this invisible interface.
It really is. It's super minimalist, entirely screenless. Its whole focus is exclusively on low-friction thought capture. The creators describe it quite evocatively, I think, as a mouse for voice.
Yeah, mouse for voice. I like that.
Yeah. The device features a really discreet, touch-activated microphone. You touch it, and it converts your spoken words, even whispers apparently, into text.
Okay, the touch-activated part sounds key, because it's not always listening.
Exactly. By requiring that deliberate touch-activated signal rather than continuous background listening like, smart speakers often do, they're cleverly addressing the exact privacy concerns that really plagued earlier generations of always-on assistants.
Right. Makes it feel less creepy, more palatable for personal use, especially out in public.
That activation design is absolutely key. The Ring acts as sort of an extended cell for ambient data logging. It uses an inner voice AI chatbot, they call it, to help manage and organize those captured thoughts. So instead of pulling out your phone, unlocking it, finding the right app, typing notes.
You just touch your ring and whisper the idea.
Exactly. Capture those fleeting ideas instantly, whether you're walking, driving, maybe stuck at a boring meeting. Low friction.
We're also seeing this ambient, low-friction approach in smart eyewear, too. Devices like the Lenskart B glasses are a good example. It seems the consumer trend here is moving toward AI-first glasses that focus really intensely on just a few specific low-friction applications. They're not trying to be a general-purpose computer strapped to your face anymore.
That seems to be the lesson learned. Lenskart is positioning its B glasses as more of a tech lifestyle brand. They're using sophisticated generative AI, like Gemini 2.5 Live AI, and the applications.
Yeah.
Things like seamless live translation, which is useful. And critically for mass adoption in certain markets like India, hands-free payments using platforms like UPI.
So integrating commerce directly into your perception. You see a bill, you can instantly pay it with a voice command without pulling out your wallet or phone.
That's the idea, making transactions completely seamless. And then you see a strong response to maybe the flip side of that, the privacy concerns, in devices like the Lenovo Visual AI Glasses V1. These are remarkably light, just 38 grams. And importantly, they were deliberately designed without any external cameras.
No cameras at all. Interesting.
Yeah, that cameraless decision is a very clear privacy-first signal. They rely purely on voice commands and an internal AI assistant for their functionality. So they offer things like real-time translation or even a teleprompter mode for professionals who might need augmented information delivery, but without the risk or the perception of recording the environment around them.
This whole quest for invisibility and low-friction interfaces brings us neatly to the Haptics Revolution, which is enabled by all this miniaturization we've talked about. For decades, getting true high-fidelity force feedback in a wearable, well, it required huge complex motors and really heavy battery packs. Think of those bulky robotic wrist exoskeletons you'd see in early robotics research labs.
Totally impractical for everyday use.
Yeah.
But this integration paradigm, it breaks those traditional engineering constraints completely. Research the team looked at has definitively shown that by using electrical muscle stimulation, or EMS.
EMS, like those workout belts?
Sort of, but much more sophisticated and targeted. By using EMS, devices can achieve physical assistance and force feedback effects comparable to those big, clunky robotic exoskeletons, but in an extremely tiny wearable form factor.
Wait, how does that work? That seems like the ultimate engineering hack.
It kind of is, because the wearable device itself isn't required to generate the massive physical force. It's merely using precise electrical signals to leverage the user's own existing powerful muscles. So the components needed in the device, the actuators, the battery can be dramatically miniaturized.
I see. It's hijacking my own muscles to create the sensation of force.
In a way, yes. Tiny vibration motors, or these highly targeted EMS systems, can now simulate really complex sensations like resistance, pressure, even movement, say in virtual environments. And this is vital for supporting multi-user virtual experiences, enhancing that feeling of social connection by adding tactile feedback to virtual interactions, making digital stuff feel more grounded, more real.
If you're finding this insightful, please take a moment to like this video, subscribe to Tomorrow Unveiled, and consider hitting that new hype button to help us reach more viewers. And of course, be sure to turn on notifications so you never miss an update on the future. So, okay, we've seen these two vectors: high-stakes augmentation, low-friction ambient compute. What does this all mean for, well, the future of the human body itself? The most profound vision of this integration seems to be technology that works through the body in cognition, not just on the skin, fundamentally merging our physical movement with environmental context.
And the industrial research we cited earlier provides really powerful early proof of this exact concept. Remember, the research team looked at that highly sensorized scenario, combining detailed kinetic data from a full-body motion tracking suit with specific contextual data from a sensorized glove, one designed to detect contact force.
Right, the glove that knew if you were touching something.
Exactly. They focused on complex activity recognition, like a worker doing a sequence of pick-and-place tasks in a factory setting. The real insight wasn't just tracking that they moved their arm, it was knowing whether they actually grabbed something at the end of that movement.
Context matters.
Hugely. The researchers found that adding that simple contact information, just detecting the normal force on the palm from the e-glove, significantly improved the overall recognition performance of the activities by about 3%. Now, 3% might sound small,
But in complex systems, small percentages add up fast.
They do. And more importantly, it dramatically reduced the system's uncertainty in distinguishing specific, similar tasks, like telling the difference between a pick motion and just a walk motion where the arm swings, or a carry motion versus just reaching.
Which means the AI's ability to understand true human activity, classifying it using complex tools like hidden Markov models or HMMs, it gets way better when you combine the kinetics, how the body is moving, with the context. Is the hand actually touching an object?
Can you maybe simplify HMMs for us just a bit in this context? Sure. Think of hidden Markov models as sophisticated statistical systems.
Yeah.
They don't just look at a single snapshot of data, like one position of your arm. They look at the sequence of movements over time. And they use probability to predict the most likely current action and even the most likely next action.
Okay.
So, for example, if the system sees an arm lifting, well, that could be reaching, carrying, maybe waving, lots of possibilities. But if the HMM also sees contact force register on the palm sensor at the peak of that lift, the probability of the action being carrying skyrockets. The ambiguity just dissolves. This contextual awareness is how integrated AI starts to gain genuine understanding, not just pattern matching.
That deep contextual awareness seems like the natural pathway to the next frontier. Brain-computer interfaces, or BCIs, which always sounds like pure sci-fi. But the field is rapidly moving from just research towards practical, clinical, and increasingly maybe even commercial applications.
It really is.
Yeah.
And we're seeing significant financial momentum building here, too. For instance, a company called Synchron recently raised over $200 million in Series D funding to advance its Stentrode platform.
Stentrode.
Yeah, it's billed as the world's first endovascular BCI, which means it's placed through blood vessels, typically in the brain. It's a less invasive surgical procedure than traditional open brain surgery, although still definitely surgical.
Right, not exactly a wearable yet.
Not yet. But the immediate goal is restoring hands-free control of digital devices, computers, smartphones for individuals with severe paralysis. And it's proving the functional potential of these integrated systems to restore capability.
And beyond those surgical options, are less invasive, maybe purely wearable BCI systems also picking up speed?
They are. We're seeing things like Synaptics Labs' Neuralis headset and work from places like UCLA on AI-powered BCIs. Both focus on non-surgical control of digital devices. This rapid expansion just proves the potential for BCIs to restore function, or even just deliver hands-free digital control, is expanding its addressable market fast. It feels like it's edging closer to the consumer space, slowly but surely. And this level of integration, where the device understands not just movement, but context, sequences, maybe even intent, brings us right to the core philosophical challenge of this whole new era. It's this shift from pure automation to active learning.
Okay.
Our research surfaced this really provocative question we all need to grapple with. Do we want a robot to simply automate a physical task for us? Or do we want an AI to actively teach us how to do that task better ourselves?
So instead of a robotic arm doing all the work on the assembly line, the integrated AI is guiding the human worker's arm to achieve mastery faster.
Precisely. The integration paradigm clearly favors the latter, teaching and augmenting the human body itself. New concepts in what's called embodied AI are using things like that targeted muscle stimulation, EMS we talked about,
Right.
to physically assist users in learning complex physical tasks. Maybe correcting poor form during physical therapy in real time, or improving muscle memory while you're learning a musical instrument, or even accelerating reaction time in high-speed scenarios like driving or gaming.
Okay, that's fascinating.
And the goal here is absolutely vital. It's to impart bodily knowledge that gets internalized, that you retain. While critically preserving the user's sense of agency, the skill should stick even after you take the device off.
Can you give an analogy for that?
Think about learning your way around a new city. If you use a physical map, you study it, you trace routes, you eventually internalize the geography. You build a mental model.
Yeah.
And then you can discard the map, right? You have agency. That is fundamentally different from just blindly following a GPS system turn by turn. It gets you there, sure, but you're dependent on it every single time. You don't really learn the city.
That makes sense. The GPS automates, the map teaches, and these new systems aim to teach through the body.
That's the vision.
But the moment the technology starts working through the user, not just for the user.
Well, the stakes around control, privacy, ethics, they just skyrocket, don't they?
They absolutely do. And that's why, while the technical progress is just astounding, I mean, from 0-3 text surgical accuracy to potentially reading neural intent, this integration paradigm opens up immediate, really significant non-technical challenges. These are the real headwinds. These are the factors that will truly determine the speed of adoption, maybe even the ultimate direction. And the biggest collision point, as the research team detailed pretty starkly, is the immediate ethical crisis brewing around mental privacy.
Absolutely immediate. The research team noted this chilling synchronization. The actual commercial delivery of a practical neural interface system, the one we discussed for tactical use, coincided almost perfectly with a major United Nations warning, a warning specifically about the ethical dangers of this exact type of technology.
Wow. So it's not a future problem they're warning about. It's happening now.
It's an immediate, real-world issue.
Yeah.
And policymakers are frankly struggling to catch up. The new ethical frontier isn't just location tracking anymore. It's freedom of thought and mental privacy. Experts are no longer just concerned with tracking simple data like steps or heart rate, which, okay, that's sensitive, but we kind of understand it. Now, they're deeply concerned about technologies that can directly measure brain activity, or perhaps more realistically in the near term, infer mental states from physiological signals, and could potentially be used to manipulate users through really sophisticated behavioral feedback loops we might not even be aware of.
That is a fundamentally different level of intrusion, isn't it? Tracking my fitness level is one thing. Inferring my intent or my mental state is something else entirely. And if the industry already struggled to protect relatively simple data like heart rate or location, it just seems fundamentally unprepared for this level of sensitivity.
That's the absolute crux of the issue. The analysis highlights some pretty severe pre-existing flaws in data stewardship right across the wearable sector. One study the team reviewed looked at 17 leading wearable manufacturers. It found that a large portion of them failed to provide clear reports on how or if they share user data with governments or third parties.
That's not good.
No. And even worse, many lacked clear breach notification processes in case of a security failure. If your systems get hacked, how do you tell users? Many didn't have clear plans.
So if the current infrastructure is already struggling to protect the data types we have now, it just doesn't seem ready to act as a responsible steward for, say, neuromuscular intent data from a tactical system, or the ambient inner voice audio logs captured by a smart ring.
It's a massive challenge. And the sheer complexity of this emerging integrated ecosystem only compounds this problem of data vulnerability.
How so?
Well, the fragmentation is just staggering. Data formats are different everywhere. Core algorithms like how heart rate variability, HRV, is calculated, which is a key health metric, differ between almost every device brand. Permissions models are inconsistent.
So nothing talks to each other easily.
Exactly. Interoperability is basically a nightmare. And that makes establishing universal accountability or transparency nearly impossible. It creates this kind of fractured defense against larger-scale data breaches or misuse. Okay, so we have mental privacy concerns, data vulnerability. This issue of cost, access, and control also leads us directly to the third major challenge the research highlighted: societal inequality.
Yeah, this is a big one. Augmentation technologies like the really advanced BCIs, the purpose-built medical AR tools we talked about, or the high-performance industrial glass, they are intrinsically expensive. They often require specialized training, ongoing maintenance. Consequently, they're often far more accessible to wealthier individuals, specific corporations, or well-funded government organizations.
And the danger there is pretty clear, isn't it? If performance enhancement, whether cognitive or physical, is only available to privileged groups, we risk dramatically worsening existing social and economic divides.
Precisely. You risk creating a world where success, whether professional or maybe even personal, becomes fundamentally correlated with financial means, with the ability to afford continuous physiological or cognitive enhancement, rather than just merit or effort. The research team's analysis really emphasizes that these issues of access and equity must be addressed head-on. Otherwise, the integrated future risks creating a permanent systemic divide between the enhanced and the non-enhanced.
A kind of biodigital divide.
Potentially, yeah.
But it's not all doom and gloom. The industry is responding to some of the more basic barriers, things like usability, cost, battery life, with a specific strategy, the research noted: hyperspecialization.
Yes, this seems to be the key lesson learned from the failures of earlier devices. Remember those first-gen smart glasses or watches that tried to do absolutely everything but did most of it poorly and drained the battery in hours?
Yeah, the jack of all trades, master of none problem.
Exactly. So now, by focusing intensely on a single purpose-built function, like the Superglass just handling job transcription, or the Sandbar Stream Ring just handling voice notes companies, can reduce the technical complexity significantly. They improve battery life dramatically. And, maybe most importantly, they reduce the cognitive load for the user. You don't have to learn a complex new operating system.
It just does one thing well.
Right. The strategic specialization seems to be finding a clearer path past those traditional adoption barriers for consumers and businesses alike.
Okay, so we've covered a huge amount of ground on the strapped-in future today on Tomorrow Unveiled. To try and summarize, the market has pretty much permanently bifurcated into these two main vectors. You've got high-stakes augmentation, which is all about measurable ROI, precision, performance in critical fields like medicine, industry, and defense.
Driven by clear value proposition.
Right, and then you have low-friction ambient compute. That's focused on seamless, often voice-first, almost invisible integration into daily consumer life. Minimalist design, maximum convenience.
And the technical acceleration behind both is undeniable. We're seeing breakthroughs in edge computing, in neural interfaces, in embodied AI, all pushing the boundary of what's possible for human function and interaction with technology. However, the data the research team compiled makes it really clear. The most significant headwind, the biggest obstacle for this revolution, it isn't technical anymore.
It's ethical and regulatory.
Exactly. The crucial battlegrounds moving forward will be around mental privacy, data security standards, and crucially, ensuring equitable access to these incredibly powerful new forms of human augmentation.
Which brings us to our final thought. This whole integration paradigm, it really challenges us all to rethink the very concept of agency. As these devices move from merely automating tasks for us, like, a robot doing the dishes, to actively teaching us skills, maybe via neural feedback or muscle stimulation. The critical question, maybe the one for you listening to consider, is how do we ensure these deeply integrated systems preserve and maybe even enhance our conscious feeling of control, our ability to learn and retain skills ourselves, rather than subtly imposing a new kind of technological dependency?
That's the billion-dollar question, isn't it? And we love hearing your thoughts on it. Whether you're watching on YouTube or listening on your favorite podcast app, please leave a comment and let us know what you think about the future of human augmentation and these new integrated wearables. Where do you see this going?
And if you are listening on a podcast service like Apple Podcasts or Spotify, we would be incredibly grateful if you could take just a moment to leave us a rating and perhaps a review for Tomorrow Unveiled. It genuinely helps us reach new listeners who are curious about the future. Thank you for diving deep with Tomorrow Unveiled. We'll see you next time.